Hey everyone, and welcome to This Explainer. Today, we're going to take the totally intimidating, buzzword-heavy world of artificial intelligence training and break it down into something highly intuitive and beginner-friendly. Seriously, if you've ever used a smart assistant, generated an AI image, or just sat there wondering how on earth these massively complex neural networks actually learn from raw data, well, you are in exactly the right place. We're pulling back the curtain on the core mechanic that makes the whole shebang possible. Stripped of all the confusing jargon, experts essentially just call this the guess and check loop. And honestly, it's a fascinating process to unpack. So, to kick things off, I want you to think about teaching a little kid with flashcards. After showing them enough examples, the kid just naturally starts recognizing the underlying pattern, right? This brilliant little concept illustrates a huge point. AI learning isn't some unknowable, hyper-futuristic magic. It's really just a digital version of learning from examples using labeled data. It is exactly like having an answer key and practicing a subject until you consistently get the answers right. All right, let's quickly look at our roadmap for today so you know where we're headed. We're going to see exactly how a neural network moves from a completely blank slate to a highly accurate prediction machine through this loop. We'll be covering 1. Learning from examples. 2. Inside the neural network. 3. Making the first guess. 4. Calculating the error. 5. Updating with backpropagation. And finally, 6. Overfitting and data quality. Okay, let's jump right into section 1, learning from examples. So we generally see two major learning paradigms in this space. The first is supervised learning, which uses labeled data with explicit answers. This is literally exactly like that flashcard answer key we just talked about. Supervised learning is all about human guidance, mapping inputs to known outputs. Think of it like training a model to predict a house's price based on its square footage. You already know the past prices, so you can check its work. Then, on the flip side, there is unsupervised learning. This relies on completely unlabeled data and lets the machine independently discover hidden structures and clusters on its own. For example, a streaming platform might use an unsupervised algorithm to group similar movie genres together without ever being explicitly told what a comedy or an action movie is. It just notices the patterns in what people are watching. But for our beginner-friendly journey today, we're going to focus entirely on the supervised learning method, the one where we hold the answer key. Moving right along, let's open the hood in section 2, inside the neural network. Now that we know we're using an answer key to teach the machine, let's actually trace the journey of raw data through the brain of our operation. The data enters through the input nodes, which basically act as the network's receptors. From there, it travels across this huge web of connections into the hidden layer neurons right in the middle. These hidden layers, that's where the heavy listing and pattern recognition actually happen. Finally, after all that internal processing, the information emerges as a final prediction in the single output node at the very end. As you might guess, it's roughly inspired by how neurons in a human brain fire off signals to one another. But you might be wondering, how does the network know how to properly process that data as it moves through all those connections? Well, it uses weights. Think of weights as internal influence knobs that control the importance of every single piece of information coming in. Every single connection between neurons has a specific weight attached to it, dictating whether a piece of data is highly important or, largely irrelevant. Think of it like making a decision on what to wear outside. You're going to give a lot of weight to the weather report saying it's raining, and probably very little weight to what day of the week it is. And alongside those weights, we have biases. These are another set of internal parameters. If weights are the influence knobs, think of biases as the flexibility knobs. They provide a baseline shift to ensure the network can activate and pass information along even when the initial inputs from our data are extremely low. What's absolutely crucial to take away here is that weights and biases are essentially the only things the network will tweak to learn. When people say an AI is learning, all they really mean is it's mathematically turning these billions of tiny knobs until they hit the perfect settings. All right, let's see this in action. Section 3, making the first guess. With our architecture in place and our structural knobs, the weights and biases, set to totally random starting positions, it is time for the network to make its very first attempt at solving a problem. This sequential process is called the forward pass. Here's how it works. First, the network multiplies the input data by those weight knobs we just talked about. Next, it adds the bias knobs to shift things around. Then, it hits an activation function, which is essentially a gatekeeper that decides if the neuron has enough stimulation to fire its signal forward. Finally, after passing through all those gates, out pops our very first prediction. Let's look at the actual math behind that very first guess. If inputs of, say, 2 and 3 multiply against those random starting weights, the numbers start trickling through the network, adding up along the way. But because our knobs were set completely at random right out of the gate, this forward pass ultimately outputs a highly inaccurate, totally bizarre initial prediction of 0.191. But of course, making a prediction is only half the battle. Let's move to section 4, calculating the error. So the network now needs a mathematical reality check to see how well it actually did on that first attempt. We have to compare our network's terrible first guess of 0.191 against our actual, known flashcard answer, which in this case is 1.0. By subtracting our prediction from the actual answer, we get a negative number. But to ensure we always have a clean, positive magnitude of just how wrong we are, the system squares that number. This calculates an exact error score of 0.327. So now the machine mathematically understands precisely how wrong its first guess was. Which leads us to the absolute climax of the entire learning process. Section 5, updating with backpropagation. So how exactly does the AI use that calculated error score to go back and fix its terrible guess? Well, it uses an optimization algorithm called gradient descent. The ultimate goal here is to reach zero error. The math calculates a gradient, which basically points to the steepest uphill slope of our error. Imagine being blindfolded on a rugged mountain, trying to find your way down to the lowest valley. You'd probably feel around with your foot for the steepest downward slope and then carefully take a small step. That is exactly what the math is doing here. Because we want to reduce the error, we strategically take a step in the exact opposite downhill direction. We step downwards, recalculate, and step downwards again. To actually take that downhill step, the network uses the backpropagation formula. Now, please don't let the Greek letters or the calculus terms panic you. This formula simply means we calculate a better new weight by taking our old weight and subtracting a tiny fraction of that downhill slope. That little fraction is dictated by something called a learning rate. We are literally just systematically nudging our knobs slightly in the correct direction so that the next time data passes through, the guess will be just a tiny bit better. And that brings us to the core rhythm of machine learning. By constantly looping through this forward pass prediction, calculating the error, and backward pass correction, our network slowly tweaks its internal knobs until that error shrinks down to almost zero. It guesses, it checks the error, it updates the weights, and it guesses again. What's truly mind-blowing is that modern AI models do this millions or even billions of times over at lightning speed until they become total experts at their specific task. We are in the home stretch now. Let's look at what happens when this goes slightly wrong in the real world in Section 6, Overfitting and Data Quality. Because a neural network relies entirely on the examples we give it, the training can definitely face some hurdles. If our flashcards are messy or highly specific, the AI might suffer from something called overfitting. This means it just memorizes the specific answers and all their messy noise without actually understanding the broader pattern. It's exactly like memorizing an exam's answer key without actually learning the subject. You're going to fail the moment the teacher gives you a brand new test. Conversely, we have underfitting, where the model is just too simplistic or poorly trained to learn anything useful at all. That's like trying to pass a calculus exam after only reading a first-grade math textbook. As we wrap up this explainer today, I want you to seriously consider a crucial question that stems entirely from how these machines operate. If these insanely powerful prediction machines only learn from the labeled data we provide, if their entire reality is built exclusively on the flashcards we hand them, what unintentional lessons might we be baking into their foundational weights and biases? It's a really fascinating puzzle about the relationship